Hello, my name is Taeyoung Kim, and in this video, I'll present data center networking for AI, co-designing the end-to-end network. The central claim of this work is that at modern scale, AI training is no longer just compute-bound, it is network-bound. The performance and cost of large-scale training are now dominated by how well we co-design the model, the scheduler, and the data center network as a single system. The paper first introduces the topic and motivation. LLMs and other Gen AI workloads now run on clusters with tens of thousands of GPUs, and the training jobs are network-bound. Unlike traditional cloud services, which generate many small independent mice flows, distributed AI training is a single tightly coupled application composed of synchronized collective communications. Thousands of GPUs exchange gradients or activations in periodic all-to-all bursts. In this regime, the job runs at the speed of the slowest packet. A single packet delayed by microseconds can stall a rack of GPUs and waste money and computing time. The paper then discusses the unique demands of AI workloads, starting from the parallelism trilemma. The communication patterns arise directly from how we parallelize the model. Data parallelism replicates the full model on every GPU, splits the global mini-batch, and performs frequent all-reduce operations to synchronize gradients. Tensor parallelism partitions large layers across GPUs that behave as a tightly coupled group. And pipeline parallelism splits layers vertically across stages, creating point-to-point bubbles of latency along the pipeline. Real systems combine all three: tensor parallelism within a server, pipeline parallelism across racks, and data parallelism across the full cluster. The paper also discusses collectiveness. Collective operations have to be called to for each rank using the same count and the same data type to form a complete collective operation. Failure to do so will result in undefined behavior. Among collectives, we discuss all reduce, which is central to data parallelism with reduce scatter and all gather as its building blocks. All to all is also discussed, where each GPU exchanges different payloads with every other GPU. Then the paper talks about the need for ultra-low predictable latency. Achieving microsecond-level tail latency is impossible with the traditional TCP/IP stack, which causes tens of microseconds of delay and high jitter. The first act is RDMA. RDMA NICs read and write directly into remote memory with zero copies and no CPU involvement, creating a deterministic microsecond scale path. Technologies like NVIDIA GPU Direct extend this idea further by bypassing host RAMs entirely. After the discussion on the unique demands of AI workloads, the paper discusses related work about co-design in the AI networks in three aspects. On the topology side, modern AI clusters predominantly use cloth fabrics. By building a multi-stage network from identical switches, cloth provides many parallel paths and high bisection bandwidth, well suited to all-to-all collectives. At the transport side, the ongoing fabric war between InfiniBand and RoCv2 is discussed. InfiniBand is a RDMA native lossless fabric with link-level credit-based flow control and adaptive routing. It guarantees zero congestion loss by ensuring a sender only transmits when the receiver has buffer space. RoCv2 runs RDMA over commodity Ethernet. To emulate losslessness, it relies on priority-based flow control, PFC, and explicit congestion notification, ECN. PFC pauses only the RDMA class to avoid buffer overflow, while ECN marks congestion to signal senders to slow down. Even with a nominally lossless fabric, congestion control must operate at microsecond timescales. DCQCN is the standard for RoCv2, which helps in this manner. It couples ECN marking with rate adaptation at the sender using PFC only as a last resort. This keeps queues shallow. High precision congestion control, HPCC, leverages programmable data planes to embed precise congestion metrics into packets. NICs then compute accurate sending rates to prevent queues from forming. And together, these methods protect RDMA's fragile, fast path. Afterwards, the paper talks about treating the network, the AI application, and the data center as one whole system. For example, Meta's Gen AI platform explicitly deconstructs the data center as a computer, so the scheduler, the Rails-based topology, and the application communication pattern are designed as one system. The paper then looks ahead to four co-design frontiers for future directions. The first is in-network computing with smart NICs and DPUs to dramatically reduce traffic and GPU overhead. The second is optical circuit switching. Hybrid designs like Google's Jupyter combine an electrical packet switch fabric with a reconfigurable OCS layer that establishes temporary light circuits at terabit rates for planned collectives. Then comes autonomous AI managed networks that perform predictions to reroute traffic or move jobs. Afterwards, we talk about sustainability and performance per watt. The network spine itself can consume megawatts, co-designed the applications, schedulers, and protocols for reducing energy use in the network. So to conclude, the main message of this paper is that large-scale AI has ended the era where the network is a passive pipe. The long-term vision is a fabric that is not just connected to the computer, but part of the computer. That is where the most interesting network challenges for AI will lie over the coming decade. Thank you.